All right, good afternoon, ladies and gentlemen. Let's get started. So yesterday, I don't want to get started. Okay. Okay, so we were talking on Tuesday, I guess it would be, talking on Tuesday about introducing two more regulated variables. Okay, so partial pressure of oxygen, partial pressure of CO2. These are regulated variables, so they will be involved in a negative feedback control system. Okay? You ready? Yeah? Okay, let's go. So we, in order to regulate anything, then classic system, we have to have a sensor for it. We have to feed that information back into the coordinating center, and that information gets coordinated, and then we send out, we change effectors, which then change the two regulated variables. Okay, so just like the steps we had with mean arterial pressure, we've got steps with oxygen and CO2, the same major steps with oxygen and CO2. Okay, so we should fully expect then to find chemoreceptors somewhere. That information will be fed into the coordinating center. Okay, so this was our brain stem. Okay, and then that information then is fed out to things that will change oxygen and CO2. Okay, but at the end of the day, the only thing that we can do to change oxygen and CO2 is to change respiration. The only thing that we can do to change respiration, the only physiological thing that we've done so far is contract muscle, right? So contracting the diaphragm and contracting intercostal muscles to either, we can contract them faster, right? So more than 12 times per minute, or we can contract them longer so that you breathe in longer, all right? So you increase your depth of breathing. So we can change frequency and depth of breathing here, okay? But that's really the only place that we can go. So the only effector in this system then is going to be skeletal muscle. And that would be our diaphragm and our intercostals. So those muscles between our ribs, right? We do have cerebral cortex influence on the brain stem. and therefore output to our effectors. Okay, so if we think of this override as our cerebral cortex. Okay, we have exquisite override control here. Anytime that you want to control your breathing, you can. If you want to throw a temper tantrum, you can stop breathing altogether. Okay, so really good parenting advice. If you've got a kid who's trying to hold their breath until they get something, wait them out. Because eventually, but a child wants, I guess in my case it would have probably been candy or Smarties or something. Hold my breath, hold my breath, hold my breath. Well, when you hold your breath, your oxygen and your CO2 start to change, right? Your sensors sense that. Information goes back to your coordinating center that says, oh my goodness, we got to change our effectors to breathe, but then the override is going, nuh-uh, am not. Okay, and that cycle will go around and around and around and around. Okay, and we can feel that cycle. So if you just take a breath in right now and hold it, you'll start to feel the cycle, because you'll start to feel the urge to breathe, right? So that's your coordinating saying, dang, let's go, but your override saying, no, we're not. So keep holding it. The urge to breathe gets more urgent and more urgent and more urgent, and that's oxygen and CO2 feeding back onto those sensors. Okay, breathe out. That's oxygen and CO2 feeding back onto these sensors and informing your coordinating center that something's amok and we have to change. But we have strong override. Cool thing though is, at some point, if your oxygen and CO2 get too thrown off, your coordinating center can communicate back with your override and shut it down. Okay, so you can't hold your breath to death. You cannot kill yourself by holding your breath, because eventually your brain stem is going to shut down the override. What does that mean? It means just you pass out. Your conscious brain stops, your body passes you out. As soon as you're laying down on the floor and there's no override, you begin to breathe normally again. Okay? So the parenting tip here would be then, if your child is holding their breath for something, wait them out. Just be there to catch them when they fall, but totally wait them out, because they can't take it to an end game. So don't be bullied. They're little bullies, I'll tell you. 4-year-olds. Kill me. So you can't hold your breath to death. So there is lots of influence over the coordinating center by the override, but there is also coordinating center can affect the override. Okay? And then under normal situations, other than your standard temper tantrum, anytime you're talking, you are overriding your breathing, right? Because you're taking a very controlled expiration out, and you're controlling when you breathe in order to make air flow across the vocal cords so you can make sounds. Okay, so every time you want to talk, you have to have override of this coordinating center to change when you're breathing, and to change how deep you're breathing. There would be hysterical conversations if people couldn't do this, because they would just randomly inspire in the middle of a sentence, right? I would love to be on the end of that one. So we have override can control the coordinating center and vice versa, and we have a lot of that going on a moment-to-moment basis. So let's take a little slightly closer mechanistic look at what's going on with this system. So this is the same picture, okay? This is the same picture with our coordinating center. So this is up in our brain stem. Coordinating, there we go. All right, so this is some neurons that you'll find up in your brain stem, okay? They have an override, so that's our classic cerebral cortex. Okay, and we have our effectors, so coming out of our coordinating center, nervous control over our effectors. Okay, so our intercostals and our diaphragm. Okay, so essentially how this is working is we have a spontaneous depolarizer up in the brain stem. No one's been able to locate exactly where it is, so lots of work here to do on how respiration is controlled. But there is a set of spontaneous depolarizers that will start firing action potentials about once to get you to contract diaphragm muscle about 12 times per minute. Okay, so that's your normal resting, awake respiration rate, 12 times a minute. Okay? So we have this spontaneous depolarizer, and that's feeding into neuron A in a coordinating center. So we're still up in the brain here, right? So the spontaneous depolarizer will stimulate A, okay, EPSPs here, in order to get an action potential in neuron A. Neuron A then will stimulate our effectors, all right, so diaphragm and intercostals. Okay, so we're going to have down onto some interneurons, so you've seen this type of connectivity before, down onto some interneurons, all EPSPs along the way in order to get stimulation of skeletal muscle, diaphragm in particular, and intercostals, okay? It will also stimulate an interneuron that will then inhibit antagonist muscles, so just to make sure we only stimulate inspiratory muscles and not ones that would antagonize that activity, we actually then send ultimately EPSPs out to the antagonist muscles, okay, in order to make sure that they don't contract and get in the way. So that's us, spontaneous depolarizer, contracting our diaphragm and intercostals, and we begin to breathe in. We contract muscle, right? We lower the floor of our thoracic cavity. The chest wall comes up and out. It's going towards 6 liters. Okay, so this is where we are. We're inspiring. So up in the coordinating center, there's this small central pattern generator. So you would have learned about those in Human Phys 1, where not only does neuron A stimulate the effectors, neuron A stimulates neuron B, which is still within the coordinating center. And then once we get enough EPSPs to stimulate B, B starts firing action potentials to stimulate C. Okay, lots of EPSPs. Once we get enough EPSPs to start firing neuron C, that synapses onto A, which will inhibit A. Okay, so once you get this thing fired up, it actually shuts itself off. Okay, so the small central pattern generator is turned on by a central or by a spontaneous depolarizer, and then once the whole thing gets working, we'll inhibit A, and that'll shut the whole thing down. Okay? Once we inhibit A, and A stops firing, then we will stop contracting the muscles for inspiration, and we will stop breathing in. Okay? So a small central pattern generator based on a spontaneous depolarizer that's cycling at 12 times per minute. Okay, so that spontaneous depolarizer is driving the basal rate of inspiration. And under normal conditions, the spontaneous depolarizer will be sending action potentials to A and have A be stimulating the diaphragm, and then get the central pattern generator working for long enough that you inspire about 500 mils. Okay, so this is how long that spontaneous depolarizer works is what's responsible for the 12 times per minute resting tidal volume of 500 mils. Okay, so those numbers that we set out when we started talking about respiration are all set here. Okay. Now we just talked about and we felt how if you change oxygen and CO2, then we can stimulate sensors to change and impose on this system, right? So we already did talk a little bit about how override can change and impose on this system, and that override seems to be plugged into A. So that override seems to control the central pattern generator, not by controlling the spontaneous depolarizer, but by changing the neuron A and making it either more or less excitable. Okay? So these were things that the override could do or would do. It would override the spontaneous depolarization and the rate at which we went through this in order to do things like the voluntary breath hold that we talk about. We talked about it in terms of a temper tantrum, but under normal physiological conditions, you do this every time you are talking or swallowing. This happens, okay? There's also involuntary movements that will impose on our little central pattern generator here. So involuntary breath hold, like a yawn. Okay, so lots of influence here. But that influence seems to come in to the start of that little central pattern generator into A. So then what we don't have plugged in here yet are our sensors. Okay, so I'm going to plug the sensors into this system right now, and then we'll have a little bit of discussion on those sensors, okay? So we do have to have sensor influence coming into here, because with oxygen and CO2 changing, then we want that sensory information to pop in here somewhere. We do have those chemoreceptors that we talked about on that other overhead. So the chemoreceptors, they'll be central and peripheral. The central and peripheral chemoreceptors will change their action potential frequency and pattern based on oxygen and CO2, and then will synapse onto the central pattern generator at A. Okay, so lots of influence, lots of convergence of information coming into A to control respiration. We also have some other sensors that we'll talk a little bit about. These are more protective, stretch receptors, and they seem to influence the system in B. Okay? So here you can see how a stretch receptor, it could come into B or come into C and very easily shut the system off, right? Because you're quickly in control of inhibiting the entire system, okay? So this picture, be aware, is exactly the same as this picture, but with just more information, okay? We've got our effectors, our sensors, and our coordinating center, and our override on here, just a little bit more detail, okay? Okay, so then let's take a look at these sensors. Okay, let's go there. All right, so we'll start with those chemoreceptors. Those are the ones that we will be dealing with in terms of regulation through the course. So let's start with them. So indeed, we have those chemoreceptors sensing oxygen and CO2. Centrally, we have them in the brain. All right, so these will be behind a blood-brain barrier. So they are monitoring oxygen and CO2 levels of cerebral spinal fluid. Okay. We're not going to really mess with cerebral spinal fluid, oxygen, and CO2. We are more geared to be able to think about what the oxygen and CO2 levels are going to be in the blood. Right, so that is also monitored by our peripheral chemoreceptors. All right, so we're going to find peripheral chemoreceptors, both for oxygen and CO2, in the very same places that we found the high-pressure baroreceptors. So in the carotid arteries, okay, so we seem to be particularly concerned about the oxygen and the CO2 going to and coming from the brain. And then also in the aorta, in the aortic arch. So we are concerned about oxygen and CO2 going to the entire body, the delivery out to the systemic system, okay? So we've set up a system to think about the brain and to think about the systemic system in particular. All right, so let's think about We'll pick one, we'll pick a gas, we'll pick CO2 first, think about that. And if we think about what's going on at the sensor level, that we have to be able to change the action potential of frequency and pattern of some sensor based on CO2 levels, okay? And so because we have the sensor in the aorta and the carotid artery, right, then we have to be sensing systemic arterial CO2, okay? So very specifically, we are sensing what the systemic artery CO2 is. Okay, and it has to be able to change its action potential frequency depending on what that CO2 level is. Okay, and so it's a very sensitive sensor, right? So it's very linear, and we live somewhere in the middle. Okay. Important to know that because that lets us know how sensitive we are to changes in CO2. So this would mean that very small changes in CO2 will change action potential frequency and pattern up into A, okay? So we don't live on a flat part of this curve, which would mean we're not very sensitive to this thing. We live on a very steep part of the curve, which means we are very sensitive to CO2. So we would have an action potential frequency and pattern coming from this sensor at all times then, right? So that's critical. It's not off, it's never off, right? So our PA CO2 would be under normal healthy conditions, would be that 40 millimeters of mercury, right? So at 40 millimeters of mercury, we have an action potential frequency and pattern. And if you went down to 38, you would change that pattern. And if you went up to 42, you would change that pattern, okay? So that's how this thing's gonna work. So essentially, what would happen is we would have, let's say, throw ourselves into a situation, if we had an increase in CO2 in the systemic blood, we would have an increase in action potential frequency from the sensors. To that coordinating center, okay, and very specifically, we now know it would plug into A of that central pattern generator. Okay, so that's just what we talked about before. And this would result in an increase in ventilation. Okay, two types of ways it can increase ventilation. It can increase our frequency of breathing, right? So we can go from 12 to 15 breaths per minute to change this, or the depth of breathing, 500 mils to 600 mils. Okay, there's two strategies to be able to change ventilation. So we can increase our frequency of breathing, and or we can increase our depth. Okay, so increase our tidal volume. All right. So on that sensor level, the response we're going to get is if we think of our PaCO2 millimeters of mercury, when I think about our ventilation, let's say in terms of liters per minute, okay, then we're going to get a similar relationship. Okay, it's going to get something linear, right, where if we were to increase CO2, we would increase ventilation. Likewise, decrease CO2, decrease ventilation. Now, like with the osmoreceptor in response to releasing ADH, where we had a sensitivity shift of the osmoreceptor based on mean arterial pressure, we will have a sensitivity shift of this sensor based on the amount of hydrogen ions, so based on what the pH is, okay? So if you had an increase in hydrogen ion concentration, the relationship would become more steep. We would become more sensitive, okay? If we have a decrease in hydrogen ion concentration, we become slightly less sensitive, Okay, and you already know that CO2 and hydrogen ion are related, right? We saw that bicarb or that carbonic acid relationship in the plasma and in the red blood cells when we talked about carrying oxygen and CO2. CO2 bound with water to make carbonic acid, and that quickly dissociates into bicarb and hydrogen ion. Okay, so that relationship, the presence of bicarb, directly relates how much CO2 we have in the system and how much hydrogen ion we have in the system. Okay, so when you have high CO2, you will have high hydrogen ion. Okay, so if CO2 is going to go up, you will make the thing more sensitive because they will both be in existence at the same time. Likewise, if you have low hydrogen ion, you will have less CO2. Sorry, I'll say that the other way. If you have less CO2, you'll have less conversion to bicarb and hydrogen ion. Less CO2, less hydrogen ion. Okay, so if we're going to go down this way, we will jump to a slightly less sensitive relationship. Okay, so they are intimately linked, and when we start to think about acid-base physiology, we will definitely see how those two are connected. Okay. All right, so we can change CO2. We've got a sensor that can then change frequency and of breathing or the depth of breathing. So the body doesn't choose one over the other. The body is always going to do a little bit of both. Okay, so it doesn't choose changing frequency over depth or vice versa. It's never going to do one or the other. It's going to do a little bit of both in order to fix the problem. Okay, so then let's look at our oxygen sensor. So at the sensor level, indeed we need something which is going to change its action potential frequency in response to a change in systemic arterial oxygen. That was about 100 millimeters of mercury, right? That's what we were regulating that around. Now we are less sensitive to changes in oxygen than we are changes in CO2. Okay, so there is a flatter part to this curve before it goes logarithmic. Okay. We live down here. Okay, on the slightly less sensitive part of the curve. So you do have to change oxygen a little bit more in order to get a change in ventilation than you do CO2. Okay, and that's because of the reason we are more sensitive to CO2 is because of that relationship with hydrogen ion. We are wicked sensitive to hydrogen ion. Okay, nanomolar concentrations or nanomolar changes in hydrogen ion could kill you. Okay, so we're wicked sensitive here. Less sensitive here because oxygen is just oxygen. But if it gets low enough, we become wildly sensitive. Okay, we will have huge change. If you get it low enough, we will have huge changes in ventilation for further small changes in oxygen. Okay, so there are oxygen levels that we are not sensitive to, and oxygen levels that we are hugely sensitive to. Okay. So let's do a decrease in oxygen, then is going to cause, so if we have a decrease in oxygen, we'll have an increase in action potential frequency up to the coordinating center, and that was into A. Okay, so directly into A, we know where that was going, and that's going to increase our ventilation. That's going to be the response. And again, that's going to be a combination of increasing our frequency and our tidal volume. Okay, so a little bit of both. Again, the body doesn't seem to choose one or the other mechanism. So the relationship at the end of the day looks like this if we extend it out to our changes in oxygen and how that would change ventilation. It looks like this. It has the same type of relationship. Less sensitive and then much more sensitive. So again, we're living at about down here at 100 millimeters of mercury, right? So that's what we're regulating around. If oxygen goes below 100, we're going to get a change in ventilation, and if oxygen goes above, we're going to get a slight change in ventilation, okay? So we're regulating around that 100. So again, we live about here. So critical, there's always an action potential frequency and pattern, or frequency coming from the sensor, and we're going to raise it or lower it, okay? Sensors aren't off. Okay, so those are our the chemoreceptors that we're going to play with for the rest of the course. I will introduce you to a couple of other sensors here that seem to be here for our own safety, I think. So those stretch receptors are really volume receptors. Okay, and this is the sensor that we plugged into B of our central pattern generator. Right, so you know where we're talking about from our overall. So these stretch receptors, you're going to find them in the trachea and the bronchioles. Okay, so they're in the tubes, right, where air is coming in. And they are excited as the lung is inflated. So they're excited as they're pulled out. So they're excited as they're stretched. Why they call them stretch receptors. Okay, and so the trachea is stretched and the bronchioles are stretched every time you breathe in. Right? Because remember, when your pleural pressure is going from -4 to -8 and pulling out your lung in 3 dimensions, pulling out your alveoli in 3 dimensions is pulling everything else out in 3 dimensions. Okay? So if you remember, if we had our trachea, we would be pulling it out in 3 dimensions every time when we went to inspire. And our pleural pressure changes from -4 centimeters of water to -8 centimeters of water. Okay, we change the environmental pressure around that trachea and pull it out too. Okay. So we're going to change that environmental pressure around the trachea. Okay, we would have called this transmural pressure. So it's similar to what we've been talking about before. Okay, so we change transmural pressure. And if I'm going to pull it out in 3 dimensions, or pull it out, I'm going to increase the radius of the airways when we do this, and since the stretch receptors are in the wall, we're going to stretch them. So we're going to stretch I should put the in there, stretch the stretch receptors. So the action potential frequency and pattern of this doesn't seem to change a whole lot. So when we're just doing our quiet breathing, right? So we must be living on some sort of flat part of the response curve for these sensors. But as you start to breathe in larger volumes, so let's say you were running during exercise, and you start to increase your rate of breathing, that's not going to change these all that much. But if you start to increase your depth of breathing, you are going to start to stretch these even more. Okay, so it seems to be that once you get up over a tidal volume of about 800 mils, right, so we've almost doubled our tidal volume from rest, then we start to send more information into B. That doesn't mean we start shutting the thing down. We just start to send information into B. But I think that this does start to, we can now see why we don't choose tidal volume over frequency, right? That we do have volume information coming into our little central pattern generator, so that we don't always choose one over the other, okay? So central pattern generator's got some volume information coming in, but not until we get someplace a little bit big. So high pressure baroreceptors, yeah, they're also influencing somehow the central pattern generator. So I didn't draw it on our little ABC diagram because I have no idea where this crosstalk is coming from. So the central pattern generator is just a set of neurons hanging out in the brainstem. But earlier in this course, we talked about other sets of neurons hanging out in the brainstem that had to deal with the heart, right? We came into cardio accelerator centers and cardio decelerator centers and vascular centers. There's just other centers in the brainstem, right, where we had our baroreceptors fed into those sensors. They're all close to each other up in the brainstem. So at some point, information from those cardiovascular control centers are popping out and influencing our little central pattern generator for breathing. Okay, I don't know where they're coming from. I don't know where they plug in. The only information I can find out about them is that if mean arterial pressure drops, so this is baroreceptor information, if mean arterial pressure drops and you get a drop in action potential of our baroreceptors, that information seems to feed into our central pattern generator somewhere to increase ventilation. I don't even know if this response reverses itself. So there's not much work done here. So I don't even know if I can write down that an increase in mean arterial pressure would drop ventilation. I'm not even sure. For the rules for the class, we'll say yes. But I can tell you right now, I have no earthly idea. But if you want to think, because when we start solving whole body problems, this is going to come into play. Because in whole body problems, we are going to have everything messed up. We are going to have oxygen, CO2, and mean arterial messed up. So they are going to have to intercoordinate with each other in order to try to fix that problem, right? There's some intercoordination happening right at the level of the brainstem, right? So I'm going to throw this out here right now. I'm going to drop it like it's hot because that's all I know about it, okay? Feel free to reverse it, but I don't know if that's true. But the rules for the class will say, yes, we can reverse it, and you can make that argument to me, and I would totally buy it. Don't make it to anybody else, they might not buy it, okay? But we'll work under that assumption. And then we also have some other receptors, so some irritant receptors. We talked a little bit about these already on airway epithelial cells, stimulated. They seem to be, they can be stimulated by particles, so that's the one we talked about, right? That if you're these mucus, these cells that are secreting mucus to trap particles that we breathe in. I said that it'll inhibit, it'll stimulate a cough. So if it's going to stimulate a cough, it's got to come in and interrupt our central pattern generator somewhere. It's got to be plugged in. It also will inhibit ventilation, so it'll stop you from breathing. And then it'll elicit a cough. So that information had to be plugged into A, B, or C somewhere. Just not sure where it's going in. Now the other cool thing is about this irritant receptor, it's also stimulated by chemical agents. Okay, so this is really interesting and important. Stimulated by chemical agents, and it's not related to smell. Okay, so you don't have to smell something to say, ooh, something smells weird, and you stop breathing. All right, so if you ever walk into a room or a building and you stop breathing, get out. Because that means your body sensed something. You can't smell it, your body sensed something, get out. Okay, because that's this reflex happening. There's a chemical that came in that we must have a sensor for. The body wants you to stop bringing it in, so it stops you from breathing. So this isn't a long-term fix, obviously, right? Because you can only stop breathing for about 3 to 4 minutes, right? So this will eventually be overridden by our own internal CO2 and oxygen sensors, and you will breathe in if you're still in that same area. So really critical. It's different than smell, so you might not be able to smell something going on in a room, But if you walk into a room and suddenly you stop breathing, then turn around and get out. And of course what this is protective. Obviously it's limiting your exposure of your lung. Let's say if it's a particle, your alveoli, you don't want to get particles stuck in your alveoli, right? But it's also limiting your the exposure of your entire bloodstream. Remember what we're bringing in, right? We're bringing in something which is about to expose the area of a doubles tennis court in terms of your blood to that chemical, right? So if you want something into the body fast, you inhale it, okay? Because you have massive exposure, right? But then, which is great. That's what we need for oxygen and CO2. That's a really good day if it's oxygen, CO2. Super bad day if it's something else, okay? So really important that we are vulnerable here, right? The whole system is pretty vulnerable at this level. Okay, but I didn't plug those into A, B, and C, because I have no idea where they go. Okay, so let's then start flexing a little bit of, we got a few minutes here. Let's introduce you to these guys, because these will become our friend over the next 2 weeks. So these are data taken from a human program, a simulated human program, where up to 300 variables can be monitored at the same time, and 300 variables can be changed at the same time, right? So you can really mess with this human. Unfortunately, you can kill them, so you can't mess with them too badly. So I will be bringing data that I ran from this program. We can work through problems, but we will, without these graphs, and in fact, on the final exam, you'll be asked to work through these types of problems without the graphs. We will use the graphs really to check our work, just to make sure that we're getting all the pieces that we think should be getting, okay? So for example, with this, because we're doing respiration, I've got a record of what alveolar oxygen and CO2 are, what our ventilation is, our alveolar ventilation, our tidal volume, our ventilation frequency, and our overall ventilation. This is big BV dot, ventilation with a dot on top in terms of liters per minute, okay? And I'm also tracking pH, because that will help segue us into the relationship between the respiratory system and acid-base physiology. So we're just going to keep track of it here, even though not hugely pay attention to it. So, for example, what I did with this system was go ahead and stimulate it in some way. So in this case, I changed the dead space. So we talked about dead space being about 150 mils, right? The dead space of increasing your dead space to about 225 mils is akin to sticking a snorkel in your mouth. Right? What did you do when you put a snorkel in your mouth? You actually extended your trachea by this long, right? That's what you did. I was brilliant when I was about 12. We used to live by this river, and I decided, we moved there I was an inner city kid, we moved to this river, which was totally amazing, so there's water there, right? And I'm thinking, I get a snorkel for Christmas, and life is good, and so they show me how to use the snorkel, and I'm using this little snorkel and kind of making sure I'm up at the top, but all the really cool stuff is down there, right? So wicked smart, I'm gonna make a long snorkel, right? So I get the duct tape out, and I've got PCB tubing, and I've got, I don't know what, I've got toilet paper rolls, and I've got stuff all wound together. So just obviously there's gonna be a structural problem with this thing in terms of how to keep it out of the water, right? But once you tie that to the dock, you can actually get way down there, right? Except now I've just increased my dead space to about 6 liters, all right? So obviously the problem there, I can get no new air in, right? So it's great for about 1.5 minutes, and then you gotta give it up and come back up, right? So indeed, I'd have died, and here's why, okay? So this is my massive snorkel. It didn't have to be any bigger than 500 mils, because that was my normal tidal volume. Yep. Oh, we have a technicality on my snorkel that I made. Yeah, because I made that was one.
It's 6 liters volume that you have to breathe out. But if you constantly breathe in, now I'm realizing that you have to like take your mouth out of the mouth.
Absolutely, yeah. So I mean, it's got to be new air, right? Everything that fills that snorkel out once I breathe out is all pre-equilibrated, right? So it's already visited the alveolus, and we've taken out oxygen, added CO2. So the more I breathe, it's called a CO2 rebreathe. I'm rebreathing. So the next time I breathe in, I'll equilibrate again, but now I took out even more oxygen, and I got rid of even more CO2. Yeah. So actually, it doesn't even have to be 6 liters. It just has to be 5. I've always got a residual volume, so it just has to be 5. Yeah. I don't know how many rolls of toilet paper it takes to get 5 liters of volume, but it was about 12 feet, and it didn't work at all. So we're not actually going to deal with obviously the snorkel example, because that takes my ventilation down to 0, right? So that's why I'd have died. If we just think about the snorkel, all right, putting that snorkel in your mouth is not for free, right? Because you've just increased your dead space. So your body actually has to accommodate for sticking that snorkel in your mouth. So if we think about what we did, if my alveolar ventilation was normally my tidal volume minus my dead space, and I've just increased my dead space, it should be a capital D, I think I called it a capital D before. If I just increased my dead space, I have decreased my alveolar volume, right? Or decreased my alveolar ventilation. So that's that less new fresh air coming in. So your body has to adopt to that. It has no idea you've stuck a snorkel in your mouth. Your brainstem has no earthly idea. But what will change is your oxygen and CO2. And we'll leave it till there. We'll leave it there, and we'll talk about it more on Tuesday. Have a great weekend.